morning everyone. I am Sarthak Sarkar and I am an assistant professor in applied mathematics in IIIT Delhi, and in this course on integral transforms and their applications I am going to cover about 10 transforms as well as content related to fractional calculus. So, the course is designed as an introduction to the theory and applications of integral transforms, and throughout this course I am going to do lots of solved examples using ordinary differential equations, certain boundary and initial value problems in partial differential equations and continuum mechanics. This course is a reference for the advanced study and research in areas including signal processing, informatics, communication and neuroscience, but not restricted to these areas. And throughout this course I am going to do solved examples arising in the areas of applied maths, physics, chemistry, biology and engineering, to name a few. So, the content of the course is as follows. The first 3 lectures I am going to spend some time on Fourier transform. Now, in all these transforms, besides the definition of the transform and its inverse, these are some of the extra topics I will be covering. Namely, in Fourier transform I am going to cover the discussion on the formal proofs of Riemann-Lebesgue lemma, as well as the topics related to Shannon sampling theorem, including the discussion on filter design, as well as the issue about Gibbs oscillation, which is a common headache for numerical analysts. The applications in this area include those arising in quantum mechanics, in shallow water waves, as well as specific cases including the Korteweg-de Vries equation as well as the Benjamin-Ono equation. Then I will be covering 5 lectures on Laplace transform, including the discussion on Tauberian theorems as well as Watson lemma, as well as solution to certain integral differential equations. I will also be covering a topic, one specific lecture on the topic of joint Fourier Laplace transform. Applications include those arising in LCR circuits, harmonic oscillators, Stokes, fluid mechanics problem, including those arising via Stokes and Rayleigh problems, that is via the flat plate flow problems, and those arising in solid mechanics or beam mechanics. And then I will be covering one lecture on Hankel transform, which arises mainly in axis symmetric or cylindrically symmetric problems. Applications will include problems involving circular symmetry like those arising in vibrating membrane, or spherical symmetry like those arising in acoustic radiation. And then I will be covering one lecture on Mellin transform, which arises very commonly in topics related to number theory, mathematical statistics, and we will specifically see how to sum up certain asymptotic limits of certain series. My lectures on Hilbert transforms will cover applications in fluids, signal processing and electronics. Then I will be covering one lecture on Stieltjes transform, namely the so called one-sided Hilbert transform, and in this case I will be covering problems involving averages and moments, especially those arising in solid mechanics and beam mechanics. I will also be covering one lecture on Legendre transforms, and I will cover problems including those arising via elliptic PDEs or PDEs arising in potential theory. Then 2 lectures on Z transform, where I will be discussing on the topic of dynamic linear systems and impulse response, as well as the solution to certain finite difference equation. As is the case, the applications in this transform includes those arising in communication digital systems and certain time invariant discrete systems. I will also be covering 2 lectures on Radon transform. Specifically, I am going to cover how to project my original physical function on an arbitrary hypersurface, and then applications using these transforms span in the areas of medical imaging, tomography and X-ray scans. Now, in all these 8 to 10 transforms, I will be covering solved examples via regular ODEs and PDEs, and then I will also be covering in the next 4 lectures in fractional calculus the fractional version of these ODEs and PDEs, namely the fractional ODEs and integral equations, specifically the Abel's the Abel's integral equation as well as the Wiles integral equation, fractional simple harmonic oscillators, problems arising via fractional Green's function, fractional heat equation, fractional fluid flow problems, fractional wave equation and fractional Schrodinger equation. Finally, I will be ending my lectures through 2 lectures on wavelet transform, where I will be covering discussions on Haar, Shannon and Dobeci wavelets, both the continuous and the discrete version. So, I would like to end this introduction by saying that almost all these topics will somewhere require some basic background in complex variables. And I would like to end my introduction in the words of the famous mathematician Jacques Hadamard, who said that the truth between 2 real domains always passes via the complex domain. Thank you.